for another Draft Physics video presentation. Brought to you by, fatigue. Oh, what the hell was that? Oh, I hate this damn fucking YouTube. Anyway, yes, that brings up the subject. Why did we go to channel videos? I didn't ask you to do that. Comments. That's where I was. Comments. I don't want this stupid comments haven't been responded to crap either. Oh, just so annoying. Anyway, alright, so Perspective Facts did do some little bit of research, found that you can find the ID of the spoof channel by first getting the frame source and then going through the frame source and finding this author external channel ID. So, thank you for that. At least I know I have some plan. But anyway, it still doesn't answer the question, why does it get rid of these features? Why? I mean, every good feature YouTube had, it's got rid of. I mean, you used to be able to search on a channel name for all the comments somebody's posted, and you could see their comments, and it seems reasonable that you should be able to know what some troll is doing on other channels. Why does YouTube hide that information? Why are the comments not even indexed by Google, the search engine? Aren't they supposed to be searching the internet for stuff? I mean, they can't search on their own, platform. So why are they making them anonymous and secret and all of that kind of crap? And they know who's more likely than not to be one of these trolls. I mean, they could mark these channels, and so you could know that it doesn't produce videos, that it has no content, that it's only been in existence for 6 weeks. They could give you some information so you could judge who's commenting. What's the credibility of this source of information? But instead, they just let the trolls run the show. Because again, any activity is good for YouTube. They just want to make things look like things are happening, make it look like there's views, and look like people give a shit and all that kind of crap. It's all just fake. And it's very discouraging. That's what it is. It's all so dishonest, and it exists. You can keep making these arguments about, well, is the problem the top down or is the problem the bottom up? And you got to blame the people, because the people keep allowing it to happen. They don't complain. They don't do anything. They just sit there and placate. And it's my corporation. I love it. It sent me a little Valentine on Valentine's Day. I mean, it's just pathetic to live in a world like this stupid. You're getting manipulated, and you just sit here and you do it. You let them do it. I mean, it's really gross. And whatever. All right, so paralogic. I guess that's what it is. Something that isn't clear to me is whether academic physicists are claiming to have performed the slit experiments shooting single photons. Yes, of course, they claim that. Now, the first experiment was a French guy, 100 and something years ago, and I've never seen it. I mean, there's frankly just very little of it. So I saw it once in like a documentary where some guy had it set up and they did it. The Veritasium guy on YouTube did it. I showed the image from that. That was the red thing with the bars. That was a single photon experiment. It's a little more complicated because you don't image it the same way usually. I mean, there's all kind of different ways to image the pattern, detect the photons, and they all have advantages and disadvantages, blah 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 blah. And as I pointed out, the Veritasium big disadvantage was he didn't scan a large enough area, and so he was just getting the middle portion of the two-slit experiment, which isn't very useful information, frankly. And you got to worry about what your detector is detecting, whether it's detecting, the photons you're sending, or whether it's detecting any photon, including heat, infrared. So there's lots of things to consider. But again, the fundamental problem is the nature of what a photon is, right? I mean, what we see, there's lots of photons we don't see. They're still photons in the sense that we know they can be detected by devices, and devices like a frog. A frog can detect photons we can't see. They can see them. They see more light than we see. So the whole nature of what a photon is part of the argument I'm making here, is that physics has no conversation about this idea. I mean, I can't find a single video, okay, on YouTube that has any conversation about the idea of what is a photon. I mean, how many of these nodes do I need before we have a photon? I mean, I'm the only person I think that's ever even brought the subject up. And it's kind of a real subject. I mean, they say things like you need 6 photons to see a photon. Right? They say things like that. Or I need 6 photons to see a photon. What are they talking about? And I would say that what they're really talking about is they need 6 of these nodes, okay, to see a photon. So, I mean, the conversation gets buried in all of this lack of information and this lack of specificity about what the hell a photon is. And as I pointed out, it's sort of an arbitrary thing. You know, I would argue, say, if this amplitude gets too high, you know, its polarization, you know, in some part of the photon, you know, because it does have a thing called polarization, that it's no longer a photon. So if it spreads over too much space, I mean, if it hits too many, you know, it's too fat, it can't hit the structure, the atoms, in such a way as to create the electrical signal that we're using to detect the photon. So you got to understand, we don't see photons, we see energy hit a system in a specific way, you know, with a frequency, and that triggers a response by the atoms that we see. And so this whole thing is a little bit mushy about what a single photon is. Is there ever such a thing in the fact that it's something we can so precisely control a piece of atomic structure where we can create, you know, this thing called a photon, and it's only a photon, it's only one photon, it's only one thing, when in theory, you know, a photon could be lots of stuff happening, but we're only going to see the stuff that hits a section of atoms. Okay, so there could have been a whole lot more stuff, you know, polarization argument. It could have more bits to it, just that we can't detect them because they're out of the polarization. So it's a little bit, yeah, they don't provide any real information, a real description of photon. They just use the word, but they really don't explain what they theorize it to actually be. They just talk about electric fields and different things, but they don't really say anything descriptive, and they certainly can't draw any rational picture besides doing a squiggly line, say there, photon. And that's way understated, way underdescribed. Anyway, experimenting shooting single photons, or if those are only claimed to be thought experiments. No, they're done experiments, but the thought comes into how much you understand about how possible it is to create something called a single photon. Because you have to create it with a pulse of energy that we can't even control. We can't make a tiny enough a bit of energy, electricity, that would account for the tiny bit of electricity or energy that a photon is. So we can't send in that discrete amount of energy to create just one photon. We send in 1,000,000 photons worth of energy and hope we can block all the other photons and just have one photon get through some material. But to get through the material, we don't know, maybe 2 photons had to go into a slit, you know, to create the one photon that we're going to send somewhere. And that one photon might be 2 photons, it's just that one bit is missing. And so just putting it through a filter, we could, you know, missing in the sense it's the wrong phase. We could rephase that one bit and end up with 2 photons, and we didn't know we sent 2 photons. So it's a lot more complicated. But the experiments they haven't done are the detector experiments. I can't say this loud enough. You can neither detect a photon nor can you detect an electron without doing something to it that's a lot more aggressive than just shining a flashlight on it. Okay, the only way you can see those things, it would be like seeing human beings by shooting a 10 million megawatt laser X-ray gun at them. I mean, it would just evaporate them. I mean, most of the forces, force it can't interact with these things because these things are going to be moved substantially. They're going to be pushed. It's like a 100-mile-an-hour wind or something. I'm not going to know your position if you're on 100 mile of varying wind or something like that. Your position's going to change. And so, yes, of course, I can't know it. I can't see it without changing it. So there's no such thing as detecting an electron in any passive way. It can't be done. So that's a thought experiment where they just project, well, if we turn the detector on, the pattern goes back to normal. Well, there's no reason for it to go back to normal. You could at least admit that, okay, that it's not going to sit there and put the electron back to where it would have been if you didn't disturb it, or where it would have been if it went straight through the slit or something. There's every reason to think you're just going to disturb it more. You're going to make whatever erraticness there is in its motion, you're going to make it even more erratic. All right. But yes, I mean, they really don't. They do this narrative thing. They talk about what physics is, and half the story, is made up story. It isn't a real experiment. It isn't a real event. It's just made out of, a story. Sounds good, but it isn't. It isn't real. Are they actually explicitly lying? Well, not about that, but they're lying to say they know what a single photon is. So right there, they're lying if they say, well, a single photon is a balloon that pops out of something. Because that we already know a photon isn't that. I mean, we know it in the sense I'm telling you overtly. You do realize they never talk about the length of the photon, right? You do know that, or the thickness of it, the polarization. They say the word polarization, but they don't explain how, well, yeah, that's how big the photon is. It's as big as its polarization. It can't get through something if the polarization is bigger than the thing it's going through. Anyway. About performing certain experiments. Yes, they explicitly lie about the experiments that have anything to do with detection, because none of these little bits can be detected. Now, if they said they did the buckyball experiment detected, that might have realistic hope. You might be able to shine some photons on a buckyball and bounce some off because it's big enough. Well, it's really not, though, right? I mean, see, this is the whole problem. It really has to be understood that light is, even though, light looks at things and we can see little tiny pieces of stuff, but the whole limitation of light is the fact that it does have this gigantic polarization problem. Okay, and the only way, like, say, if there was one little atom, okay, so even if I took 50 atoms would have a diameter that's still, what are we going to say, 25 times an atom, let's say one atom, that's even if it was crooked. So let's see, what would that be? So 25, it would be 12 nanometers. That's it. Okay, so 12 nanometers would be the size of the buckyball. All right, so in the light, we know visible, regular red light, 500 nanometers, okay, of polarization. And so in the polarization is really where the quanta is. The quanta is somewhere in that range. So you got to understand that at best, only one of these little bits, okay, or two, are ever going to hit the single buckyball. So all the buckyball can do is break a photon. It can't make one. Okay, so you're going to have a real hard time seeing something. So I drew this way off scale. I mean, the real scale would be something like this is the buckyball, and this is the photon. Okay, the photon is big. The little buckyball of atoms is small. So how do you see a small thing with a big thing, right? You can't do that. So this is why microscopes can't see, past a certain limit. It's because the photon is actually a huge thing. And you can't bounce it off something unless you're bouncing off something that's at least as big as it is. So once you get, below you get into these, 500 nanometer kind of sizes, unless you're looking at a whole structure, you're not going to be able to get your photons back. So you're really not going to be able to see, you can only see so much detail with a photon, because it's going to get broken by things smaller than it. All right, so Dave says, that would be the premise of DraftScience argument. 100% of videos of him breaking down for you on his channel. Well, the point is we do have to be accurate about which things I'm saying are fake and phony and which things aren't. I'm saying the evidence they're using to draw their conclusions is insanely weak for how strong they believe. Like I said, the Eddington experiment, the whole gravitational lensing thing. The flaws in the logic are gigantic. The whole idea of measuring 1/10,000th of the width of a proton with an instrument where you can't even bounce the ruler, the light, off the mirror with that kind of precision. You can't know how deep your light's going to go into the mirror with a 10,000th of a photon guarantee. So how can you measure 1/10,000th of a proton when your ruler, your light beam, can't reliably have the same distance each time it bounces back and forth 1,600 times? I mean, the logical disconnect they're gigantic logical disconnects, and it's disgraceful that all these coward physicists that I've contacted won't answer any of these questions. They won't explain how these are paradoxically oxymoronic. You can't have it both ways. You can't have it this way. You can't make this claim with any kind of credibility. All right. So anyway, Paralogic says, please forgive my having missed a lot of the content from this channel over the years. I didn't have time to follow it properly until lockdown. I've been keeping up with if you've been doing the recent videos, then you should have been able to make this distinction of what experiments. I mean, look, I think I was pretty clear what experiments I was saying were fake. So, I mean, I have to say that, frankly, if you watch the last video and I showed the chart and the whole thing, the comments on this video, I mean, the two subjects are different subjects. The subject of creating a single photon is a different subject than the subject of detecting photons or detecting electrons. And I clearly stated the detection part is clearly a fraud. It's not even, it's not even theoretically possible. There's no theory for detecting an electron because we have no source of energy fine enough, small enough to hit it with that doesn't completely disturb it. It's like seeing a Volkswagen by hitting a Volkswagen with another Volkswagen. You're not going to see much except little, shit. You're not going to learn anything. But you're not going to get any energy back. You're not going to get a reflection back. You're going to get pieces of shit back. All right. I've been keeping up with the recent videos and was hoping he could quickly clarify this issue. Well, none of these issues are all that. It's all this quickness stuff that's the problem. 5-minute video physics. Sorry, that isn't going to get to the subject. All of them are a little bit nuanced. And they just turned into some sort of particle wave conversation. It's a lot more complicated than that, and so you can't do physics on the cheap. I mean, you can do it cheap, you can do it economical, but you can't do it for free. I mean, you can't just do, I read a book, pamphlet, 10 minutes, and I'm a physicist now. That ain't gonna happen. Hope that's not too irritating. Well, it sort of is. I mean, it's irritating that you couldn't make a distinction between these two different subjects. And, I've drawn it so many times, this idea of what is a photon. I've asked the question and drawn the pictures and said, are they telling you what a photon is? Are they honestly describing it? By saying photon, have they given you something to see in your head? And they really haven't. Okay. How do you produce a single photon? So this is going to be just so bad. So, so this Jerry Hall, you're just one of these, these dopey, duped evangelists for, this evil cause. You're just sitting here polishing the Pope's, seal-skin booties. Is that all you got to do with your life? Is just to keep defending crap? I I mean, you're always doing this crap. I mean, how do you produce a single photon? Question mark. And then this video is supposed to have the answer, and it's the typical piece of steaming crap. It has nothing to do with single photons. It has to do with a completely different subject. So this is called physics world. Yeah, like we shouldn't be skeptical right there. But it's just crap. So I'll play this piece of crap, and I'm just saying, why do you think this answers any questions? What knowledge did you gain by watching this video? So it claims that it's going to answer the question.
Single photons are individual particles of light, and they're useful not...
Okay, so they're individual particles of light. Now, does that say anything to you? What's a photon then? Oh, it's this big round thing and it just flies through space? Does it say anything right there? Did he tell you what a frickin' photon was? No. So we start off with just saying it's a particle of light, whatever that means. It's not. Okay, clearly it's not. So it's just, it's not, you can't use that definition and be serious. It's a garbage definition. I mean, I don't even know how to, a school of fish is a blob of fish. I don't know. I don't know. No, even that's more descriptive.
Not only for studying fundamental physics, but also for transmitting and processing information in extremely powerful ways. So
more just gibberish about it does amazing things. We've done amazing things with our amazing amazingness. We 10,000th of a proton measured that distance with our amazingness. Just horse shit.
I think that it's very easy to make single photons.
Oh yeah, you think so. Okay, yeah, I bet you never did it in your life.
All you do is you take a light bulb and you send a beam of light from that light bulb through a pair of sunglasses.
Right, and what's a beam of light? Okay, exactly. What is a beam of light? A ray of light, do you mean? Or do you mean a whole bunch of rays of light?
And if your sunglasses are sufficiently thick, then once in a while you'll find that on the other side of the sunglasses you get a single photon arriving. But these...
Yes, right, but you haven't even described how the sunglasses are actually working, okay, which is how they're actually blocking the light. By what? Creating little holes? Well, what do little holes do when a photon goes through it? Oh, that's right, it creates this scattering problem, you know, all these diverging photon. And so am I really seeing a photon? And again, what is seeing a photon? How big a surface does a photon have to hit? How many atoms worth of surface does a photon actually land on? When somebody says single photon, does that mean a single electron got hit? No, that wouldn't be rational. No, a whole big piece of surface of atoms got hit, and those atoms had to be hit just the right way to create a vibration in crystal. It's usually a crystal that can detect these things. And that's registered as a photon because there's an electrical signal.
Photons are randomly distributed in time, and that makes them not very useful for implementing any information process.
So this is really stupid because he says they're randomly distributed in time. Yes, and your example is going to have the same limitation. So it's hilariously incoherent.
Tasks that we might like to do. So instead of that, what we can do is we can use a process called parametric down conversion, which involves generating photons in pairs.
Which is a pile of crap. But anyway, let's go ahead and let him say it.
And we take a laser that emits a short pulse of light.
What does a short pulse of light mean? So again, with this, there's no rationality here. They can't make a gigahertz, okay, frequency. So they can't create a pulse of light that's a gigahertz short, which is, you know, the frequency, the wavelength of light. We don't create light by putting an actual light frequency into the antenna, so to speak. See, radio, we can make a wave that runs, you know, an electrical signal that's the exact signal that we want the antenna to produce. But light, we can't do that. We have to essentially just send in electricity and heat the damn thing, and by heating it, just randomly create, you know, the signal we want. We can't just say, oh, we'll put in 20 volts at 43 gigahertz and we'll produce red light or we'll produce green light. You know, can't do that.
And we send that into a crystal that allows us to generate new frequencies of light that weren't there before.
So this is just, this is a silly description of the concept. So the concept is they put in an ultraviolet signal, a blue laser light. All right, so a frequency like this, and what they do is they end up getting 2 new photons out, okay, that are half that frequency, so they're twice as far apart. Okay, so they're twice the frequency. So this is frequency, 2. Okay, this is 1F. So you have 1 of the frequency here, and you get 2 of the spread out. So you're getting the same amount of energy in the sense of the same number of little bits would be the idea. But obviously this would have to be a longer, this pulse. And this pulse could be many, many millions of photons. So there's no way to control how many millions go in. And so the idea is that it goes into the crystal. They don't have a perfect explanation of any of this stuff. But the idea is the higher frequency light goes in, and what comes out as a cone. Okay, so you have to sort of understand that some of the high frequency stuff goes straight through and comes out the middle. Okay, so it never gets changed. But if it does change, if it does scatter, what it'll do is it'll create a photon that that'll end up going somewhere on this cone. So you don't even know where it's going to come out, right? And so this has nothing to do with creating single photons. This won't make single photons. You put 1 million in, you might get 50,000 coming out of this as red light, okay? And the blue light, you'll get the other 950,000 will come out as blue light. But this doesn't create 1 photon. This doesn't help you create a single photon. It has nothing to do with fixing the problem he drew there, where, well, we could get this many, we could get 10, we could get 15. We don't know how many are going to come out, and we don't know what pulse rate they'll be coming out. So again, understand their pulse is going to be some very long thing, because we can't make a tiny enough pulse, and so there's going to be potentially photon there, photon there, photon. The pulse, anywhere in the pulse, there's going to be potential for 1 million wavelengths worth of light in the pulse itself. The pulse is huge in space, and so there could be a photon here, there could be a photon here in time, it could be anywhere in this time scale. So this is just more of the same crap. 2-minute video, minute and 34 seconds of just wish and wash. There's no facts in this mush.
And if we arrange things carefully, these new frequencies of light are generated at half the incident frequency. And
that's exactly how it functions. That's right. Yes, it's energy conservational, but it's that's all it is.
That corresponds to generating pairs of photons at the same time in this.
So they don't know if it's at the same time. It could be just scatter in a sense that the bits are hitting different electrons, and they could be getting scattered at different points. There's no way to measure something like at the same time. They don't have any tools that can measure that.
Crystal. So when our detector over here tells us that 1 photon has arrived, then we know that there's a single photon ready to be used in our experiment.
Yeah, ready to be used. Isn't that just quaint? Obviously, it's all happening so fast that there's no way to get this signal saying, "Oh, there's a photon." Well, guess what? It's too late to do anything about it. It's not going to help you any, because it's going to take at the speed of light time for that signal to get to your processing unit to say, "Hey, guess what? There's a photon." We have to do something, and you got to send the signal back. You get it at the speed of light, and the photon's moving the speed of light. So the whole thing is just such mush. They're working with thousands of photons at a time. They're not detecting a single photon and then saying, "Oh, a single photon is ready to be used." I mean, this is just such an oversimplification, just kind of making it seem like they have such control over these systems. They don't have any such control. So it's just more hype and bullshit.
And we can use those single photons both for studying quantum physics and also for transmitting and processing information.
Yeah, you can just make up stories about, oh, you're quantum entangled, mishy-mushy, photons have spin, all this other crap. That's just crap they made up. So that was just terrible. So way to go, Jerry. So why don't you explain, Jerry, how that video has something to do with single photons when nobody's using it to detect single photons, and I think you know that. Anyway, pretty much they say science is more art than science, but personally I think that science, it's more religion than science. Well, it's clearly they're actively invested, okay, in the mystery parts, right? I mean, it's all obsessed with black holes and singularities and big bangs, and then you get into all this entangled crap and many worlds and mysteriousnesses. I mean, all the hype is about questions they should have answered a long time ago. Wave particle duality crap. Again, it wasn't, it's Newton knew about the basic concept. And if Newton had, any of this information about, all the information we have about the fact that there existence of protons and electrons, he wouldn't be sitting there doing nothing and still saying, well, it's a photon, an arbitrary amount of this in a size that's arbitrary and, So this science is lame and silly. Wave particle duality should have been ruled out a long time ago. They should have just looked and figured out, well, what the hell is it really? Because they already have enough information to dissect it. It's clearly particles that can sometimes look like a wave, and that's it. But they never act like a wave. Again, you can't shoot a laser at a laser and get anywhere. Anyway, it's just so disappointing. I've worked as an assistant at a certain lab from Colorado for nearly half a decade. Every time one of my superiors needs their papers to be peer-reviewed, they tell a bunch of assistants like me to sign them. I'm not even a real biologist, nor did I read what I was signing. Nevertheless, well, that's another problem, the whole notion of peer review. How does peer review work? Well, yeah, they have a couple of reviewers who are smart, at the top, okay, that are getting a salary, or, they're paid something by the magazine, to be available to critique. So they have a couple of people with real degrees, up here, they're available for editing. But when you submit your paper, it goes to some smo, okay, so some douche who probably doesn't have any kind of degree or any kind of anything, and he basically just says, oh, well, that's not what my guys say is good stuff, so I'll just throw it in the garbage. I mean, he doesn't have to understand any of it, right? I mean, he doesn't necessarily have enough competence to judge what's coming in, so how can he know garbage from not garbage? I mean, frankly, if I was a judge and sitting there and some douchebag like the Broly, right, says, well, because photons can sometimes look like a wave, let's say that Volkswagens, wait, what was I saying? Oh yeah, Volkswagens are a frequency and such. Every time you have a momentum that something's moving, therefore it has a frequency. Because sometimes momentum can be consistent or proportional. Your momentum is proportional to your frequency. That is, frequency will tip something over, so it looks like real momentum. Therefore, we're going to say that every momentum carries with it a frequency. I mean, that kind of logic. If that's the best you can, I would be throwing that paper in the garbage. Dirac's antiparticle. Yeah, I'd throw that one in the garbage. So a lot of papers that should have got thrown in the garbage. Einstein's bent space. Yeah, I would have thrown that in the garbage. Come on, you can't do better than that. What do you mean the space is bent? What the fuck is that? It's not a force. That's not a reason for something to move. The bent three-dimensional space? Come on. It's silly. Well, anyway. So yeah, there's no even talking about this whole, peer review. It doesn't have anything with peer review. It has to do with Pope review. It has to do with, is it consistent with the Bible? So if the theory is not consistent with the Bible, then yeah, throw it in the garbage. All right. They'd tell a bunch of assistants like me to sign them. Okay. Nevertheless, I had to do it in order to keep my job. That's what passes for peer review study in biology these days. Well, I mean, obviously the peer review thing, the whole idea that they found that many of this science that they thought was good science, it survived peer review, and then when they re-reviewed it, they found none of these experiments could be duplicated, the theory was a pile of shit, blah blah. Like 30 or 40% of the statistical data was crap. So yeah, when they videotape the peer review, when they do something to apply scrutiny to the peer review process, it is found to be substantially lacking in its capacity to tell shit from food. Anyway, let's see. Dave says, Paralogic, not at all silly. Well, not for me anyway. I was just trying to be helpful. So I don't know what Jerry said. So I don't know. But anyway, just so irritating. So I don't even know if I want to bother with this Linda engineer, because this is gibberish, I think. Can it be some light bit? So look, I already have an explanation that really works well. So again, I don't have to do this searching for an answer. My answers already fit. And you're telling me what? What do I need some other answer for when this works? This little quanta theory of light thing, it actually works and explains this. The two-slit experiment explains why the math needs to have 4-point sources and all that. It explains all of that. So what do I need to fix it for? Anyway, can it be some light bit for up-faced surface? For up-faced surface go down and down-faced surface cause some bit go up, and then phase is okay for light to show. Maybe she's talking about film. I mean, I did say how the film has to flip. I didn't really literally mean something flips, okay? I'm just saying that the film has a chemical composition that can either look opaque, like dark, or light. So what it happens is that you hit it with enough energy, it oxidizes, you could say. And so it turns dark. And so the little bits on the film are just turning, grades of light and dark based on how much energy hits them. So it's almost like it was heat, and you know how heat can change the color of something. Well, the same thing is sort of happening to the little bits of the film. So the film has all these different sized little blobs of crap. And if enough energy hits them, photon, then they'll change from light to dark or dark to light. Maybe that's what she's talking about. I don't know. I think the lens in eye which image go backwards like mirror. Yeah, it's old news. The reversing of the image. So what? Do pattern go backward if each slit is different size from other? Well, see, that's the whole point. It doesn't matter, frankly. So the only time you're going to notice it would be as if you had a slit, a diffraction gradient or something. And then you made it some kind of odd shape, like you put the light in, straight on one side and curved on the other, or some kind of image, in the light itself. Then you might see that like if I did make it a D shape, the D shape would end up going this way. Okay, and the ones on this, they go round on this side and then flat or on this side would, I don't know how to, they'd all be this way. Well, anyway, it doesn't really matter. Obviously the slit experiment isn't, a single slit. The argument is just that there's electrons here and it just scatters everywhere. All the bits are going everywhere. So whatever data was in the beam, it is lost. So there's no way you could take an image and send it through the single slit and have any hope of regaining the image, because you're making new photons out of pieces from very different locations. Where with the multi-slit, with a lot of slits, that doesn't have the same effect because it's all light from here ends up, yes, going to another location, but it's in the same orientation as the light from here. So they do it progressively, so they'll all line up again. So you have laser beam in, you have laser beam out, laser beam out, laser beam out. If that's even what you're talking about, but I don't really know. Okay, so enough of comments. Yeah, so we'll go back to the Yale thing. So I'll go find that, and we'll do some more of that. Alright, leave us continue and such.
Omega, as you know, is 2 pi f. So here's what I'm telling you. If you send light of a known frequency, a known wavelength, and you make it extremely dim, and you put a photographic plate, and you wait till something happens, what happens is not a thin blur over the whole screen. What happens is a hit at one location. And what comes to that location seems to be a bundle of energy and momentum, i.e. a particle. Right? When something is...
Okay, so again, i.e. a particle, but that's not what happens. So again, let's just go through this one more time. Light is not received in one tiny location, like one single electron or something. It's received on a surface, and the surface has a bunch of atoms, and the light is falling on a surface that contains maybe 1,000 atoms. Okay, and that surface interprets the photon. That collection of atoms reacts in a way that creates electricity, a current, and so a photon isn't as tiny as the energy in it. The energy in it is tiny, but the photon itself isn't that small. Okay, it's got a, it's a big thing in terms of what it actually does on a surface. It's big, not small, compared to the little nuclear bits. So photons don't hit single atoms. They don't hit single electrons. They don't hit tiny locations. They hit relatively big locations. I mean, it's still tiny from our perspective. I mean, an atom is to the Earth what an atom is to an apple what the apple is to the Earth. So I mean, there's a ton of atoms. So atoms, 2,000 atoms is almost nothing for us, but it's a lot when you're thinking about where it's, the fact of all the places you could land. It's like you're landing, not on a tiny thing.
In the face, it's got energy, it's got momentum. So this film is getting hit at one point by a particle, and what we can say about the particle is the following. It has a momentum. It has the same momentum every time.
So this is the funny part, right? The same momentum every time. But see, that's the catch. It can't possibly have the same momentum every time if you're going to say frog can see ones we can't see, right? So again, what he's saying has the same momentum is the quanta of the photon, the hump, if you want to say that in your wave theories. These little humps have the same momentum, all right? But the photon has a ray length. Okay, and the fact is we see it in chunks of that ray. So if it has 6 chunks, the atom says electricity. If it gets another 6, it says another hunk of electricity. It gets another 6, another hunk of electricity. So it's measuring a certain amount it needs, the minimum amount for it to trigger. So you're really just saying what pushes it, what tips it, what the thing is there to get hit. You hit it with energy, it moves a little bit, it rocks back and forth. And how many times do I have to hit it to finally get it to tip over? And the truth is, for our human eye, you have to hit it that 6th time for you to tip it over, to make the switch contact, to make it the thing say, yes, photon, electricity. So when there's 6 of them, electricity. There's 6 more, then electricity. 6 more, electricity. Okay, you'll just have a constant pumping. All right, but it has to happen in units for the human eye of 6, and units of 3 for a frog, or 3, maybe 4 for a photomultiplier. Everything has a different trigger that says, yeah, I saw that, I saw that, I saw that, I saw that. But it can be a continuous ray. It can be a ray of millions of these photons in one ray. You can just keep pushing. The ray can be, you can keep pumping electricity into a material and just keep producing a continuous stream, okay, of bits. And, you know, there's lots of 6 chunks in those bits.
You get this hit, you get that hit, you get that hit. As long as you don't screw around with the wavelength of incoming light, the momentum and energy of each packet is identical.
See, that only has to do with what we're using to receive it. So the amount of stuff you have to hit, like the photographic paper, each clump of stuff that's going to change color is a different size. So obviously it's, you know, it has a different amount for each one to turn color. You need a different amount of light to hit it to change the whole thing, to get it to flip from light to dark. So it really always has to do with what you're using to collect the photons, how consistent the energy is, so to speak, and how much you're absorbing of a photon, how many photons you're absorbing, so to speak. But yes, if you measure it just by the quanta, they're always consistent. They always carry the same amount of momentum. The little clumps, the little hills in the wave.
So it's more than saying light seems to be made of particles. Made of particles, each one of which carries an energy and momentum that's absolutely correlated with the wavelength and frequency.
So it's not absolutely correlated. It's only correlated to the fact that that's what creates electricity, which makes them able for us to see them. The energy of them is heat. So the fact is, if you measured photons based on the heat they produce, then you'd have an even more accurate total of the energy transmitted. But we can't measure heat that discreetly.
Now let me remind you that omega equal to kc for light waves. We've done this many, many times. That means the energy is h bar omega and the momentum is h bar k are related by the relation E equal to P.
Right, so he's just taking the speed of light and a constant k, which would given you the Planck constant, essentially. So he's just saying how many little bumps go through at the speed of light. All of them have the same momentum. So they're constant in that sense. But you can vary the number of those little bits in an amount of time. And when you do that, the time factor means there's more energy. So the higher frequency the light, of course, it delivers more energy per unit of time. But it's only per unit of time. Over a long period, you could have a very short ray of ultraviolet light and a very long ray of infrared, and the two would have the same energy. It's just they're spread over a different amount of time.
So these particles have a momentum which is related to energy by the formula E equal to Pc. When we go back to your relativity notes from the last semester,
I mean, P is momentum, so he's just saying energy equals momentum times the speed of light. Yes, so we're using that constant, but it's sort of irrelevant. So you're just saying energy equals momentum, which means speed, velocity times mass. Now, there's no velocity times mass involved in a frequency. We already know that all the little bits are moving the same speed, and all the little bits have the same mass. So really, the variable is how many little bits in a period of time.
you'll find the following relation is true. Any particle, E squared equal to C squared, P squared plus M squared C to the 4th. That's the connection between energy and momentum. Therefore, this looks like a particle whose M is 0. If M is 0, E equal.
Right, so this is where they get silly, right? So they could make M, the mass of the photon, infinitesimally small. They could just say it has a Planck mass of 10 to the minus 34th or something. They could give it any kind of mass. And if they gave it any kind of mass, then this could make some kind of sense. But they give it 0 because they want to annihilate, half the equation. but it shouldn't have zero. It can't have momentum and have zero mass. It's retarded.
The PC. So these particles are massless, they have no rest mass, and you know something with no rest mass, if it's to have a momentum, must travel at the speed of light. Because normally, the momentum of anything with mass is mv.
But it doesn't matter. It's speed of light with no constant, with no mass, doesn't mean anything. 0 times the speed of light is 0. So again, they can't just keep saying it like it makes sense. It doesn't make any sense.
In the old days, divided by this, after Einstein, and if you don't want to have an m, and yet you want to have a p, the only way it can happen is if v is equal to c. Then you have 0 over 0, there is some chance. And nature seems to take advantage of that 0 over 0.
Well, 0 over 0, you have some chance. So he's saying that somehow makes sense. 0 over 0 makes sense. That's a real thing. 0 over 0. As opposed to, some other silly 0 relationship. Any 0 is going to ruin the equation. So why are you putting a 0 in there?
0. These are the massless particles. So these photons are massless particles.
So again, silly, in my opinion, thing to say. Make it the tiniest mass you want to write, 10 to the minus 675.
So what is the shock? The shock is that light, which you thought was a continuous wave, is actually made up of discrete particles.
Okay, so when he says light is, he should say a photon is made out of some other kind of tons, little quantons, little bittons, little clumptons, something. They should be called something. They're bits that make up the photon. Okay, but a photon is not a thing in it of itself. It is not like an electron. It is not some indivisible thing. It's clearly a composite thing. And this is the conversation they just don't have. They just say the word photon like somebody's supposed to, oh, this is a photon. No, it just flies through space. It's an ultraviolet photon. No, it isn't. It needs to have, you need more information. Because this, if you say a human sees this, or a frog sees it, maybe a human doesn't. So that explanation just isn't good enough.
In order to see them, your light source has to be extremely weak. Because if you turn on a light source like this one, millions of these photons come, and the pattern is formed instantaneously. The minute you turn on the light...
So we shouldn't say instantaneously, right? That's just, obviously none of this happens instantaneously. It's all that C thing. So that's a mistake.
The film is exposed, you see these dark and light fringes. You think it's happening due to waves that come instantaneously. But if you look under the hood, every pattern is formed by tiny little dots, which occur so fast that you don't see them. That's why you got to turn down the intensity to actually see that. When you see that, you see the...
All right, so tiny little dots means groups of atoms receive the photon and it create some sort of change, some sort of electrical or magnetic, some sort of effect that we can detect. But we have to convert it into the effect. There's no seeing the photon without creating the effect. The photon has to cause something for us to say, it's a photon. So automatically, it's sort of dependent on our ability to see something tip. So it's sort of clumpy in the sense that stuff can be hitting it, and we don't see this. We only see this when it tips, right? So that's the only way we can see is something tipping. We can't see this. So it's like we're saying, it doesn't exist when it's doing this. It only exists when it knocks it all the way over. So of course it's going to look like a clump from that perspective. So I don't want to imply that I'm arguing against clump theory. Okay, I think it's clumps. But the point is obviously it's kind of a mistake to say, it's a clump because our detectors only detect clumps. That's the problem. Your detectors can only detect clumps. So yeah, of course you're calling it a clump. But it could be not a clump that the actual thing is coming in. So you haven't converted the force into a clump by saying my detector only sees clumps. So this is another kind of sloppy deduction.
Corpuscular nature of light. But here is the problem. If somebody told you light is made of particles and it's not continuous, it's not so disturbing. Because water, which you think is continuous, It's actually made of water molecules. Everything that you think is continuous is made up of little molecules, and in a bigger scale, much bigger than the atomic or molecular size, it looks like it's continuous.
Right. So why don't you just point out, though, that, yeah, that's the catch here. We're basically describing a medium that light's traveling through. We're trying to tell you that there's some sort of thing of, atoms like, that somehow the atoms are jiggling, and that jiggle is what we're seeing it changing. There's not something actually moving from point A to point B. We're just sending a signal through a bunch of ether. But they don't say any of that crap because, yeah, that would sound kind of primitive.
That's not the bad news. The bad news really has to do with the fact that if you have these particles called photons, if it really were a particle, namely a standard garden variety particle, what should you find? If you emit a particle from here, and only one slit is open, it'll take some path going through the slit and it'll come there. So let's say on a given day, 10 photons will come here. Well, let's say 4 photons will come here, with this one closed. Then let's close this one and open this one. In that case, maybe 3 photons will come here. Well, let's say again 4. Now I'm claiming that when both are open, I get no photons.
Right, you're claiming it, and that's the whole problem. So we're right back to the same argument again. He's saying, okay, that he has some evidence, real experiments, real hard, discrete data, proving that. And my whole argument is, no, they don't, because when they actually do the experiment, this is the Veritasium one, yeah. Well, unfortunately, he's got ads on it. So, but I showed it the other day. So it's just what they haven't ruled out is that no, they're just seeing the addition. So they're creating one. They're throwing a bunch of broken bits. With from the 2 interior surfaces, and then the 2 exterior surfaces are going to throw another bunch of broken bits. And the fact is you can make 4 times as many photons with those 2 different sources. So you can make photons that were invisible much more visible by adding more bits. The more bits you add, you multiply the number of photons you could resolve. And that's all. That explanation works to explain that it doesn't really, you open a second source and you get less light. No, that never happens. You open the second source and you see more photons. You don't see less photons anywhere. You just add more to the parts where you do see them.
How can it be that when you open a second hole, you get fewer particles coming there?
So that's what they haven't proven, that there's any fewer, okay, that you ever take any light away by opening the second slit. They've just assumed it, and because water does it, because sound does it, therefore light does it. And they haven't demonstrated that light does it.
Particles normally either take path number 1 or path number 2, either through this slit or this slit. To all the guys going this way, they don't care if this slit is open or closed. They don't even know about the other slit. They do their thing, and guys going through this slit should do their thing. Therefore, you should get a number equal to the sum. But you don't.
Okay, he says it. They don't. He doesn't have evidence for that. So that's an under-experimented claim. Okay, they don't have hard experimental data that demonstrates that. Well, I showed this, but I'll show this one again. Because it seems to be necessary to do this. So this page should load correctly. There it is. Okay. So you can see that when they actually do this experiment where they put a slide and opening across the 2-slit experiment, and so you're seeing it with essentially 1 slit open and then seeing it with the other slit open and with both slits open. So it's doing exactly what he's saying. And what you're seeing is that when both slits are open and you're getting the pattern, there isn't any clear darks between the little circles. The circles don't have hard dark lines between them. They have much brighter spots, okay, on top of the old pattern. So clearly the first pattern is still there, and they're just adding more light to make the new resolution. So they haven't subtracted any light, they're adding light. And if you make the pattern so you can see those little dots, and they did this over again and did it with less light, so there was hard darks between those lights, I would argue to you, you wouldn't see the other pattern. the other pattern would not be enough photons to resolve, and so you'd see nothing, 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 and then you'd see the two slit pattern, and then you'd see nothing. So I'm just saying this is the experimental data. You can't claim that, oh yeah, when I opened the second slit, all of a sudden this spot became black. No, it didn't. It didn't become dark. Just become, the next slot next to it become much brighter. That's all that happened. The spot next to it became much brighter, so you could see the difference between the two, but you didn't make it darker. You just made the seat next to it, brighter. Somewhere around here. Oh, that's not it. Maybe this is it. Nope, that's not it. That's not it. I keep missing here. I didn't think it was this far down, but I guess it is. Where the hell is it? I was just playing the damn video. It's got to be here. Okay, there it is.
In other words, for particles which have definite trajectories, opening a second slit should not affect the number going through the first slit. You understand that? Particles are local. They're moving along and they feel the local forces acting on them and they bend or twist or turn. They don't really care what's happening far away with the second slit maybe.
All right, they don't feel any local forces. So let's understand they are a force. Forces don't interact with forces, so they don't feel anything. They can only hit electrons. Then they feel something. Then something radical happens. But till then, they just go from point A to point B in a straight line. They don't feel anything. They don't bend anywhere. They don't curve anywhere. So that, again, is a statement he's making. I don't think he has any evidence to back it up.
Open or closed. Therefore, logically, the number coming here must be the sum of the number that would come with one open and two open.
Right. And I think the evidence indicates that's exactly true. That there is just more light. And that's, if you really do the experiment, that's the result you're going to get. And you won't have any location where all of a sudden there's less light. So it isn't consistent with waves in mediums.
How can you cancel a positive number of particles coming somewhere with more positive number of particles coming from somewhere else? How do you...
I know. Well, how can you do it? Well, you can only do it in your imagination, because in the physical reality, you didn't do it. You didn't do it with an actual experiment. So this is just all part of the story. They tell each other. His teacher told him, his teacher, they just tell them these stories as if this is the way it works, when that's not really the evidence.
Get a zero. That is where the wave comes in. The wave has no trouble knowing how many slits are open, because wave is not localized. Wave comes like this, it can hit both the slits, and certainly cares about how many slits there are. Because there's only one, that wave will go, you'll have some amplitude here, which is kind of featureless. If that's open, it'll be featureless. If both are open, that'll be interference. So we need that.
The point is they will interact in this space. Waves can interact with waves. The forces are now moving matter. Moving matter can bang into each other and cancel. Forces can't cancel. They have to get to a piece of matter before the addition is done. So a force pulling one way on something can't cancel with a force pulling the opposite way on something until the force actually gets to the matter, and the matter does the addition and says, okay, it's the same. I got pushed this way and then I got pushed this way, so I just ended up back in the same place. But it has to get to the matter before the matter can do the addition. The other examples are mediums. They already have matter doing the addition. So the addition of the forces is being done by the medium, the water molecules or the air molecules. But there are no air or water molecules between for photons. Those things don't exist as mechanisms. I mean, except when they're being transmitted through those things as transparent mechanisms. And then you have effects where, the light progresses at half the speed or 40% of the speed.
Wave to understand what the photon will do. Because when you send millions of photons, and if you get the pattern like this, let's say you sent lots and lots of photons, and you got a pattern like this. Now I'm going to send million plus one photon. Where will it go? We do not know where it will go. We only know that if you repeat the experiment a million times, you get this pattern.
Right. And we only know that if you do it a million times, that way you're getting lots of pieces. And if you send one photon, the problem is once you scatter the pieces, there's no way to reconstruct it because you're not taking more pieces from other places. If I scatter a single photon, it means I've scattered all of its quanta. So its quanta have all gone to different locations. Well, if that's all there is, they won't reconstruct a photon because they've all been scattered. So if I send 1,000 photons, well, then the pieces from each photon can add up in different locations and create new photons out of the pieces. So the experiment won't work with single photons. So if you actually do the experiment with a real single photon generator, that is something where you've demonstrated that you have created very rare photons, very intermittent photons, I'll predict you won't get any pattern. You'll get some photons that go straight through the slit, yes, because they don't get hit by anything. They don't hit the electrons, so they don't get broken. So there'll be a few that go straight, but you won't get any of the scatter, because the scattered ones have to have a partner. They have to have pieces coming from another source for you to reconstruct those photons. Without pieces from another source, there won't be any photon.
But on the million plus 1th attempt, where it'll go, we don't know. We just know that the odds are high when the function is high, or the intensity, and the odds are low when the function is small, and the odds are 0 when the function is 0.
So they're just doing statistical math, right? That's all this physics is now, is right? It's just statistics and probability. That should be a completely separate subject than physics, frankly. I actually took a class in high school, and it didn't have any physics in it. Because, it's just about establishing probabilities and knowing what numbers to multiply by what numbers to figure out how improbable or probable something is. But again, saying that this is running on that system, when obviously it runs on it in the sense that if I randomly throw things, in the air, and they'll create a pattern, and so I have 20 things on the ground, well, I can know that if I randomly do the same thing again, there'll be some chance that a certain number of them will fall exactly in the same spot that the other shit I threw fell. And so eventually, if I do it enough times, I can stack up 6 things in one bucket. One bucket will have 6, whatever I'm throwing in the airs. And some other bucket might have 1, and there'll be a distribution.
So the role of the wave is to determine the probability that the photon will arrive at some point on the screen.
So they don't say the role of the wave. That's the wave function. So that's after it's gone through the slit and they've turned it into 2 wave functions. That determines the probability.
And the probability is computed by adding one wave function to another wave function and then squaring. So you got to be very clear. If someone says to you, is the photon a particle or a wave? Make up your mind. What is it? Well, the answer is, it's not going to be a yes or no question. People always ask you, is matter made of particles or waves, electron particles or waves? Well, sometimes the vocabulary we have is not big enough to describe what's really happening. It is what it is. It is the following. It is a particle.
So it's he's blaming vocabulary. No, the problem is that you aren't explicit enough in your description of what a photon is. Again, you don't deal with something as fundamental as its length. It's a fundamental feature, and its width. Polarization. You don't deal with those subjects as real subjects. That photons have a real dimension in space, and you don't account for their real dimension in the space they're traveling.
In the sense that the entire energy is carried in these localized places, unlike a wave. When the wave hits the beach, the energy is over the entire wavefront. This wave here is not a physical wave. It does not carry any energy.
Right, so it's not a physical wave, but in a sense it has to be if you're going to make it a medium. So if you're going to make it a medium, you still have to call it physical in some way. I mean, is the field part of physics? I mean, you can't, how do you get away with this idea, well, it's not physical? What does that mean? I mean, how do I describe water waves if I say the water isn't physical? That doesn't make any sense.
It's not even a property of a beam of photons. It's a property of one photon. Here's what I want you to understand. You send one photon at a time, many, many, many times, and you get this.
Right. So the idea of what one photon is a whole big problem. If you're not going to deal with the subject of its dimensions, then you claiming you've sent one photon seems like a completely unsourced claim.
Pattern. Each time you throw the die and ask where will the photon land, this function is waiting to tell you the probability it'll land somewhere. So
right, and I can give you an explanation for where it's going to land in the sense that I'll tell you that when you're sending this thing called a photon, you're never sending one photon, that you're sending energy, little discrete bits of stuff, and that the little discrete bits of stuff are going to encounter whatever you put in their way, okay, and the discrete bits are coming in all kinds of different ways, and some of them are going to get scattered on the edges. Some of them are going to go straight through, and the fact is that whatever you sent here, what you're going to receive here is going to be a composite of that. That is, they're going to get pieces that were way over here are going to be here, and a piece that was way over here is going to be over here. Those two pieces are now going to be a photon, okay? But they weren't in any way related to each other when they started. One of them was way over here, and one of them was way over here, and they were in a different place in time, and so their timing is completely different because this one happened, okay, much earlier because it's going a longer distance. This one went through at time 1, and this one went through at time 15. Okay, so they didn't go through at the same time. They aren't from the same, so they weren't even in the same row. They weren't in the same horizontal space or vertical space, and now they're going to end up being put into an arrangement that is going to have the right sequence to say flip, trigger, tip, photon. So now it's a photon, but it's a photon made of things that happen in discretely different places in both space and in time. Their time is different. They're from different sections of time, and they're from different sections of space. And so this is a new photon made of parts that were created here. Parts go through the system, parts go through the space, and you make a new one out of the parts. You break the cars, you knock all the wheels off, all the fenders off, all the headlights off. They're all going to all these places. You have headlight here, you have headlight here, you have tails, you have all the pieces here, and there's places where you're going to put the wheels together, the frame together, the steering wheel, the roof, and you'll have a car again.
We have to play this game in two ways. It is particles, but its future is determined by a wave. The wave is purely mathematical. You cannot put an instrument that measures the energy due to that wave.
Good. I mean, it's good that he says it's purely mathematical because, yeah, you can't draw it. It doesn't make any physical sense. You know, it can only make sense as some mathematical thing because you can't draw it. Because if you try to draw it, you'll see that the point sources aren't where the waves are supposed to be. And the real part that's breaking stuff is actually the surface. The surface is where all the action is.
It's a construct we use to determine what will happen in this experiment. So we have no trouble predicting this experiment, but we only make statistical predictions. So if someone tells you,
okay, so yeah, well, we only make statistical predictions. Well, the predictions don't mean anything because yes, anybody can do that. Any moron can go to Las Vegas and watch a roulette wheel and figure out, hey, these numbers all come up about the same number of time per hour. You know, there's just as many 22s as there are 21s, as there are 20s, you know. So yeah, I predicted that now that I figured out exactly what it does. Well, that's not much of a prediction, is it?
I got light from some mercury vapor or something. It's got a certain wavelength, therefore a certain frequency. I'm going to take two slits, and I'm going to send the light from the left so weak that at a given time only one photon leaves the source and hits the screen. What will happen? We will say we don't know what it will do. We don't know where it will land. But we tell you if you do it enough times, millions of times, soon a pattern will develop. Namely, if you plot your histogram on where everybody landed, you'll get a graph. It's the graph that I can predict. And how do I predict?
So again, they don't predict that graph with their generalization of two waves. Their two waves can't predict the actual pattern. So that's part of the fraud here.
That graph. I say, what was the energy momentum of your photon? If it was P, I will introduce a wave whose momentum is 2 pi h bar over P. Oh, I'm sorry, I forgot to tell you guys one thing.
Yeah, well, that generalization, again, that's the generalization of these two waves, and it's the wrong answer. It doesn't predict the right pattern.
Apologize. I've been writing h bar and h. I should have mentioned it long back. H bar is h over 2 pi. Since the combination occurs so often, people write h bar. So you can write lambda.
So yeah, I don't know why the 2 pi. The 2 pi always kind of is curious, right? I mean, pi is a wavelength difference, so what do you need two wavelength differences for? It's a little strange. But anyway, doesn't really matter. All right, so we'll quit here at 22 and pick it up next time or something like that and such. So till that next time, all I can do is reason with you. That's all I can do. There's reason to doubt what conventional physics says, because obviously this is the simplest of experiments. You really can't get any simpler than that. 2 slits, sending something through. And look how inspecific, how, and just overtly wrong what they say about just this simple experiment. If they can't describe their simple experiment, their fundamental cornerstone experiment, accurately, why do you trust them when it comes to Higgs bosons and gravity waves and black hole singularities and all of that crap? Why are you trusting their judgment when they're showing you how sloppy they are in drawing conclusions?